That movie.
This chapter is about nebulae. So chapter 34, what's a nebula? A nebula, Sam, is a big ball, a big cloud of gas and dust in space. And they come from when stars explode. Stars will explode and shoot out a bunch of gases and dust, and they sit there in space for millions, even billions of years. But if given the right kick, maybe another explosion somewhere that pushes them together, they'll start collapsing and can form a new star. And that's where our sun came from. Our sun came from a huge cloud, a nebula in space, that collapsed to form a new star. And we'll talk about that here.
Is it hotter in that state? Like in the nebula form? Because it's like perfect blue.
Well, we'll talk about that. When it's glowing, it's hot. But when it's not glowing, it's cold. So it starts really cold and not glowing. This one's glowing a little bit. So let's first talk about a couple of famous nebulas out there that you'll probably see pictures of. This is called the Eagle Nebula. It's also called the Pillars of Creation. It was one of the first pictures Hubble took, and was beautiful, and is one of the most famous photographs on Earth now. Yeah, this is it's called the Eagle Nebula. Wow. And it's huge. It's this huge gas cloud in space. And to give you an example of how big it is, you see that little finger right there? That finger is as big as our solar system.
Wow. Oh my
right there, that little finger. All the way out to Pluto is right there.
Is there a dark horse?
So you can see, yeah, we'll see that in a minute.
Wait, so how did they form that photo?
They took a picture of it with the Hubble Space Telescope. It looks out in space, and it sees this little patch of space, and it zooms in on it, and there it is. That's really, if you were to look in the sky with the naked eye, you couldn't even see that. It's so far away. And if you look with a telescope, you can barely see three little things sticking up. With one of our telescopes, you can barely make it out. And if you use a Hubble Space Telescope, that's a lot better. Did y'all know the Hubble Space Telescope was better than that one?
Yeah.
More expensive, too.
How expensive are we talking?
The Hubble?
$10.
Several hundred million. Maybe $1 billion.
It's a lot of money.
It's a lot.
I figured it'd be that much.
But I always keep this in mind. You know how much an aircraft carrier is? Several,
600 million?
maybe 100 billion. So 1,000 times what the Hubble might cost. So you always got to keep in mind how much we spend on other stuff. I think you could bump that. If you could bump NASA's budget by one aircraft carrier, we would have 100 times the amount of space research that we have now. 100 times the employees. One aircraft carrier.
We should start a petition.
Yeah, they're not going to listen.
There are petitions out there.
But I do think this is pretty important on the scheme of things. An aircraft carrier also important. I'm not against defense, but sometimes I think we get a little crazy on defense. That's enough. Let's not talk politics today. Anyway, this is the Eagle Nebula, very famous nebula. Let's see video footage of it. Music by Breathe.
That's what he showed us when we could
What? Wait, so all those dots were light years away, right?
Yes. Yes.
It's too big.
Okay, here's this is Orion. There's the belt of Orion, and there's the shoulders, and sometimes they show them with a bow. But anyway, there's the this right here below Orion's belt is the Horsehead Nebula. It's located right there. Again, you can't see it with the naked eye. You have to have a telescope to zoom in, and if you have a real good telescope like the Hubble, that's what it looks like. It looks like a horse's head. It's another famous picture that Hubble took. That's your favorite one? Now, I want you to notice how dark it is. It's dark like that. It's a dark dust cloud. It's really cold. Anything that's dark is cold. If it's hot, it would be glowing, but this one's dark.
Kind of creepy.
Yeah, I wouldn't want to be on that.
Oh no, I was looking at it. Like, it sounds good. Hey, we're not looking at it. Oh my god.
Many ads.
Lock this production. Still in my thought.
The constellation of Orion is one of the most recognizable patterns in our night sky.
They're doing it from the back.
Within its boundaries lies the Orion Molecular Cloud Complex, some 1,500 light years away. Inside this complex, on the farthest eastern edge of Orion's belt, is one of the most photographed nebulae in astronomy, the Horsehead Nebula. This nebula was first recorded in 1888 by Scottish astronomer Willis at the Harvard College Observatory, and ever since, we have been captivated by it. The red or pinkish glow originates from hydrogen gas predominantly behind the nebula, ionized by the nearby bright star Sigma Orionis, which is really a young 5-star system just out of view. The darkness of the Horsehead is caused mostly by thick dust, although the lower part of the Horsehead's neck casts a shadow to the left. Streams of gas leaving the nebula are funneled by a strong magnetic field. Bright spots in the Horsehead Nebula's base are young stars just beginning to form. Since 1888, this has been our main view of the Horsehead Nebula, and it has become an icon. But in April 2013, astronomers using the Hubble Space Telescope released another view, one that only Hubble's infrared cameras in space could provide. Here is the Horsehead Nebula in the infrared. In the Hubble image, the backlit wisps along the Horsehead's upper ridge, illuminated by Sigma Orionis, can be seen. Two fledgling stars peek out from their now exposed nurseries. This nebula gets its shape from powerful forces within the stellar cradle. Harsh ultraviolet radiation from one of these bright stars is slowly evaporating the nebula. Gas clouds surrounding the Horsehead already have dissipated, but the tip of the jutting pillar contains a slightly higher density of hydrogen and helium laced with dust. This casts a shadow that protects material behind it from being stripped away by intense stellar radiation evaporating the hydrogen cloud, and a pillar structure forms. The Hubble Space Telescope has been providing us with groundbreaking science for 2 decades. And every once in a while, it takes time out to give us a portrait of familiar friends in a completely new light.
Yay, Hubble. You know, it's going to be replaced pretty soon by the James Webb Space Telescope. That's going to give pictures like 50 times as magnification.
Are they building that now?
Yeah. Pretty much built. They just got to get it launched. It was supposed to be 2017 last I heard. So,
Yes.
The Horsehead Nebula, and this one right here, is called a dark dust cloud. That's hard to say real fast. Dark dust cloud, dark dust cloud, dark dust cloud. Try it.
Dark dust cloud, dark dust cloud.
See, it's not easy. Also called a dark nebula. It's a dense ball of dust and gas in space, and it's so thick you can't see through it. Now you can see some stars on the edges because that's where the dust is thinner. And I want you to notice something. Those stars are red looking. That's the same reason our sunsets are red, because the blue, as the light from that star right there comes through the dust, the blue is scattered out, and all that's left is the red. And so that's why when the sun comes up, it looks red, because the blue is scattered out because the sun is low in the sky and it's got a lot of atmosphere to go through. And the blue gets scattered out and all you see is red. Now when the sun's up high, it doesn't have nearly as much atmosphere to go through, the light to get to you, because it's not going along the edge of the atmosphere, it's going just straight through it. And you see it, the light as white. But when it's on the edge, it's going through a lot of atmosphere, it's seen as red. And so the same thing with these, and we call that reddening. Reddening is the red that you see. And so we know that this is a big, thick cloud that's thinner on the edges, and that's why it looks red there. A little tiny dark dust cloud in space has one of the coolest science names I know. A Bach globule. Isn't that a cool name? A Bach globule is a tiny dark dust cloud in space. And a bigger dark dust cloud in space is a dark dust cloud, or a dark nebula. But if it's a tiny cloud, it's a Bach globule. I just thought you might want to know that term, Bach globule. Sounds pretty cool. Now, if one of these clouds starts collapsing, it heats up. As the cloud collapses, it heats up because the molecules are hitting one another, creating friction. Rub your hands together real quick, create some friction. Can you feel it heat up? That's good. It's good to do that and then touch your face. I always enjoy doing that. It's a good way to warm yourself up. So, as these dark dust clouds, there's a dark dust cloud right there. You see how dark it is? That's dark and cold, just a few Kelvin temperature. Almost absolute zero, real cold there. But as they come together and fall together, they start to heat up and become red. A red nebula is called an emission nebula. And if it's glowing red, that's hot. It has to be up to 3,000 Kelvin to start glowing, and that's really hot. And then it'll start emitting light, and actually stars will form inside these. As these nebula continue to contract, they'll get so dense that they'll form a star. And if the starlight is bouncing off of gas, it comes back as blue. That's called a reflection nebula. A reflection nebula is blue, and an emission nebula that's glowing is red. So you can have different looks in the sky, but you can see this is blue. That's because light is bouncing off of it and reflecting off of it, and we see that as blue light. The red light continues on through, and the blue light bounces off. That's why we see our sky as blue. Because when the sun is over here and it's hitting the molecules of the sky, some of the sunlight, the blue light is reflected down towards you, and the red light continues on through. That's why the sky is blue. Try and explain that to a 4-year-old when they ask you why the sky is blue. They might have trouble following. The red light goes on through, the blue light is refracted or reflected, and you see blue. Same thing's happening here. Blue light is reflected, and you see blue.
Whoa.
So, I want you to think about this big ball of gas and dust. Yes, question?
Why is it that the blue light is the color that's reflected?
Has to do with the wavelengths. Blue light is shorter wavelengths, and shorter wavelengths are more easily bent.
Okay.
Longer wavelengths, like red light, is harder to bend.
Okay.
So the longer wavelength kind of continue on through, and the shorter wavelength is not around. That make sense?
Yes.
By the way, that's how I dance with Ziggy's. I do this, and then I do this. And they're going, oh, he's doing the wavelength dance. Only the real smart ones there do that. There often aren't a whole lot of those. It's 2 a.m. But anyway, so imagine this big ball of dust and gas collapsing and collapsing, and as it collapses, it picks up some spin and becomes, as it gets more dense, it becomes what's called a protostar, a spinning disk. And as you know, if you take a ball of dough and you throw it up in the air, it starts to spin and gets thin. And so that's what's going on here. Like when you're making a pizza, that's how you do it. You spin it around and it flattens out. The same thing happens with the gas in space. It spins around, it flattens out. It heats up in the middle so much that that can start to fuse and become a star. This is how our solar system formed. The star forms in the middle, and the planets form around it, with what's left here of the gas and dust on the edges. And these things shooting out, those have a name. They're called bipolar jets. Can you say bipolar jets?
Bipolar jets.
Those form because of magnetic fields. That the spinning material has huge magnetic fields. We talked about spinning hot stuff, spinning molten stuff, has huge magnetic fields that cause material to shoot out either end. Those are called bipolar jets. And when we study black holes and things, those become really important. So we're getting towards that. But some material shoots out the ends, other material spins around, and the material at the very center fires up and becomes a star. And so here are the stages of star formation. They're actually numbered. Stage 1 is a giant cloud. Stage 2, it's getting even smaller. Stage 3, it forms this protostar, which is a disk of spinning material. Finally, at stage 5, it lights up in the middle, and you have a young star. That's how our sun formed. Went through these stages. The entire thing takes about 10 to the 7th years. Do you know what number 10 to the 7th is?
It's like 10 million.
10 million years. Yeah, it takes about 10 million years to go along. And actually, this stage itself takes 10 million years. It might take 100 million years to get to this stage. Anyway, you want to see star formation video?
Yes.
Pretty much out of time here.
Nebulas house baby stars in every spiral arm of the galaxy.
These regions are the nurseries for new stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink.
Stars are made out of gas, basically, and our galaxy has gas. In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk, and it's from this gas that new stars are born.
By observing nebulas at different stages in their evolution, the story of a star's birth begins to emerge. It all starts inside a cold, dark cloud of dust and hydrogen gas, where a quiet tug-of-war begins. The cloud wants to dissipate, like smoke in the air, but gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. Gravity wins, and the material crunches down into a disk that is the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it gets denser and denser and hotter and hotter. Until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium, and with a burst of nuclear energy, a star begins to shine.
These stars eventually get their nuclear fires going in the core. And when they do, they heat up, they can expel the material that's around them so that it kind of clears up the neighborhood.
Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns.
It blows away the gas, it blows away the dust, and it lets us see this beautiful new thing, this place where the star has been born.
Lifetime is too short to witness the wonder of a star's birth in the spiral arms. But by speeding up millions of years of cosmic time into just a few seconds, we can see one star born after another.